Let's begin here. So please, at the end of the lecture, don't let me forget, I have corrected, well, slightly corrected homework 1 to return to those of you who handed it in. So as I mentioned on the first day, we're not really grading the homework carefully or in any detail because there are solution manuals all over the World Wide Web. And in fact, we allow you to copy answers from those. Could you be quiet, please? Ready? Okay, so you can, you're allowed to copy homework from any place, from your friend or from the web. We don't recommend it. It's a poor way to learn the subject. But anyway, we're not checking your answers carefully. You should check, but you should check them carefully against the answer sheets that are posted. Anyway, so these were just sort of checked for completeness. We want to give you, in some years I have said to students that you don't even need to hand in the homework, just do it, and then they don't do it. So this is a little game where we say you hand it in, we'll check it for completeness, and then it gets you to do it. Anyway, there's, today we had the first section of the course that, remember, is optional. I hope you all got email about that. So, but it'd be great if you could go. I think you'll learn a lot by going and participating, doing practice problems. Also, we're giving bonus points of some unspecified nature. So if you're a grade grubber, it will help you if you go to the sections. But I think it will help you learn the subject. Okay, so anyway, let's begin our lecture today. Yes, question? Good. If you go to, you mean like if you go to 2 in a week or something? I don't know. That's an interesting idea. Yeah, you could rack up lots of points. I don't know. I don't even know what I'm saying about the bonus points. I just want to give you some incentive to go. So, you know, I mean, if you want to go several times, maybe that's good. I don't want to say no to that. I don't know what the answer is to that question. Yes? So, okay, the question is, how do the sections work? I don't know how they work. We never had them before. Let me just give you the little educational philosophy here. That this is a subject that I think I've said a few times looks kind of easy. And when I'm doing it at the board, I think you'll find that it looks easy. And when you read the book, it looks easy. But then I have found when people take tests, they often make surprising mistakes and show a lack of understanding that always makes me wonder, what am I doing wrong as a teacher? So I think what I'm doing wrong is that I don't give you enough chance to be active. That is, you're just sitting there passively saying this subject is cool and you're taking notes, but you're not actually doing enough. And so the homework is one place to do something, but now that there are all these answer manuals on the web, I'm worried that the homework has no activity function either. So I want to give you some way to be active, and because all kinds of educational studies show that's what helps people learn. So my thought is the sections should be a place where you can go and do whatever it takes to help you learn, which might be that the section leader will give you practice problems, other problems from the book. You could work in little groups. You could just ask questions. You could watch computer simulations. You could do computer simulations if you bring your laptop. So I don't really know. It's up to the section leaders what they're going to do. And it's up to you. I mean, you can suggest to them what you think would be valuable. But we got 2 really good teaching assistants who are going to give you 2 sections a week. And we'll give you points for going. And I don't know what we're going to do in there. But doesn't that sound reasonable? There should be a way to, what do you think is the most helpful? I mean, do you want to do more problems? That's usually the best thing to do. And you know, if your friends are there, you could talk to each other, and it's kind of interesting to do that. So yeah, that's one option. We can do it that way. Anyway, I don't know what we'll do, but the first one was this morning at 9. There's another one tomorrow at 9. They're both with Isabel. She's the one who suggested doing it that early. I said nobody's going to come at 9. But 4 people did come. And yes, thank you. But then there's Alex is giving sections later in the day at, I don't know, like, I forget, 6 or 7 or something. That's on the web, so check when he's doing that. Also, we try to schedule them before the homework. So if you're just worried about doing the homework, you may use the section for that purpose. But we also have office hours for that purpose. Any other question about this thing of the sections? Okay, so now let's leave all that administrative stuff and start the lecture. Here's our topic for today is a model of an insect outbreak. So in the book, it would be section 3.7. And the summary of what you're going to get out of this is that it's a nice bifurcation problem. We've been talking about bifurcation theory now for a few days in the context of one-dimensional systems. And what will make this one different from what we've looked at before is that it involves two different parameters. That is, in the last bifurcation problem we looked at with the bead on the rotating hoop, there was just essentially one control parameter, which was the speed of the rotation of the hoop. Whereas here we're going to have two parameters, and it also will bring in a new phenomenon for us, which are discontinuous jumps. That is, we're going to change a parameter continuously, but the response of the system will be discontinuous. And that's an interesting and important kind of effect that can occur in bifurcation theory and in the real world. So the paper that this lecture is based on is kind of a classic paper in the mathematical biology literature. It's by Don Ludwig and his collaborators. It's from 1978. Appeared in the Journal of Animal Ecology, and it's volume 47. Page 315. So if you're interested in ecology or population biology, I would definitely recommend looking at it, or bifurcation theory. It's a really nice, clearly written article. It's intended to be pedagogical. It was at a time that population biologists weren't so familiar with nonlinear dynamics, and the authors were sort of trying to teach their colleagues about the value of this way of thinking that they espoused in the article. Okay, so the problem that they're addressing has to do with a pest called spruce budworms. Which, I don't know, we have anyone here from Canada? There's someone. You ever heard of spruce budworms? What part of Canada? Okay, so I don't know if they affect you there. It's much farther east and north that this is a problem. Have you ever heard of them? No. You have heard of them. Yeah, they're kind of a big deal in the Canadian timber industry because they can wipe out the forest when there's an outbreak. And so in eastern Canada, or the northeastern part, also in Maine, in America, they, there are these disgusting little slugs that crawl around on the leaves of balsam fir trees, and they eat the leaves. And eventually, they kill so many leaves that the trees die, and then the forest can collapse. So they can sort of munch their way through a forest in about 4 years. Whereas it might take the forest decades to recover, many tens of years. And so, and what's particularly weird about this is that this keeps happening, that there are these spruce budworm outbreaks every few decades, and then it's a massive disaster financially and ecologically. And people aren't exactly sure why do they occur periodically. I mean, they're not perfectly periodic, but there's a kind of typical time scale for which they recur, and why, what's causing it, and what could we do about it? I mean, that's what people are especially interested in. How should we, should we use certain pesticides, or what should we be doing to stop this? Well, anyway, so there are complicated models with hundreds of variables that people run on computers to try to think about this, where they look at the dynamics of the budworms and the predators that eat them and the forest itself and the different types of trees. But Ludwig and company recommend just thinking at first about an extremely simplified, unbelievably simplified model, where we're just going to look at one variable. In their paper, they also consider a larger model with 3 variables. But for us, let's just start with this. N of t is just going to be the population of budworms. And let's assume that they obey a logistic model. So n dot is Rn 1 minus n over k, which we talked about earlier in the course as a model for how populations would grow when they are competing against each other. That is, the budworms are competing against each other for this resource, the leaves that they like eating. And there's this number k, which is the carrying capacity. That's a measure of how many budworms can be supported by the forest. But that's not all that there is in this problem, because there's also birds which like to eat budworms. So they're predators. And so we want to include a term, P of n, predation by birds. So the growth of the budworms obeys logistic growth if in the absence of predators. But then this is a term that causes death of budworms due to being eaten. And the biologists have certain arguments about the form of P of n. P of n is a nonlinear function of n. It's not just that the more budworms there are, the faster they get killed. The birds are a little trickier than that, it turns out. So the claim is that if you look at P of n versus n, this is an empirical thing. You'd have to study the behavior of the birds to really get this. But apparently the way it works is that P of n has this interesting nonlinear shape. That it starts out very small and stays very small until sort of a typical number, which we'll call A, where it turns on sharply. And then after that, at some point it saturates and reaches a level that we'll call B. And so if you want to make up a little story about why the predation term would look like this, you could say, well, suppose there's not many budworms. That is, n is small. So the birds are flying around looking for food, and it's hard to find any budworms. So they just decide, well, I'm going to eat something else. And they do. So the predation is not very high. It's like sort of the birdworms are flying under the radar. They're not getting noticed. But then once there's a critical number of budworms, or actually the better way to say it is, what the birds are really sensitive to is the number of budworms per leaf. So they're looking at density. And if they see a leaf covered with budworms, that gets their attention and they go in there and start eating. And so once there's a certain critical density of budworms, which would translate in this picture to more or less this number A, then they start going after them. And so then the death rate goes up and up the more budworms there are, because there's more budworms, they're going to be dying faster, until at some point the birds are eating as fast as they can. So it saturates at some level that we're going to call B. So that is, if there's 1 million versus 2 million, they just can't eat any faster. All right. So I hope that that looks believable. And then, anyway, algebraically, we're going to write it in this simple way. I mean, there's various functions that have this type of shape. But for algebraic convenience, we'll write it like this. Bn squared over a squared plus n squared. And you can see that that does have the properties that we mentioned. That is, it's at low values of n. Say, if n is much smaller than a, then you can think of this as sort of a constant times n squared. I've exaggerated the flatness in this picture. I mean, this would look locally parabolic near the origin, which this looks flatter than that, but okay. So this would be sort of parabolic up near 0, and then at large values of n, where n squared dominates a squared, then it'll just asymptote to b. So this has the right qualitative shape, and we're not interested in anything quantitative here. Yes?
Would you expect the p curve to change over time as the population of birds might be affected by non-dimensionalizing?
The question was, would we expect the p curve, the predation curve, to change over time because of possible changes in the bird population? Yes, I think you would. And so there's various other things happening in the model that we're ignoring. As you say, the birds have a population of their own, and so that will change on some time scale. And the forest has its dynamics. I mean, as the forest is being degraded by being eaten, other things will be changing. So we're ignoring these slower time scales of the dynamics over which the bird population changes and the much longer time scale on which the forest changes. So think of this as governing what's happening over a matter of a few weeks during which this outbreak is going to happen. And so on that time scale, both the forest and the bird populations are so slowly changing we can pretend that they're constant. But if you really want a detailed model, you'd have to take all those other dynamics into account, which is what's in the computer models, and also later discussed in the paper, in Ludwig's paper. But at the lowest level, it's like this. Okay, and this is already pretty rich because, as you can see, we have 4 parameters, R, K, B, and A, which is a big parameter space to explore what's going to happen. So we've got A, B, R, and K. And I'm using capital letters for these parameters. They all have units on them. That is, they're not dimensionless. And you will remember that in our last lecture we talked about how it's often convenient to non-dimensionalize a model, to scale it, to get rid of these parameters that do have units, to see, first of all, makes the algebra simpler, but it also lets you see what's essential. And so we want to ask, what's the dynamics of this system like for various parameters? So you could ask what happens if the growth rate of the budworms is faster, that is if R is bigger, or the carrying capacity goes up or goes down. Anyway, there's a lot to change. And it turns out you don't need to explore all 4 dimensions of possibilities. There's only certain combinations that matter. And that's another thing that the non-dimensionalization reveals. So since this is kind of a large parameter space to explore, it helps to non-dimensionalize the system. And what we'll see is that even though it looks like it's a 4-dimensional parameter space, in fact, it only really boils down to 2 dimensions of parameters. So let's see that. Now, here's a little tactical point. That is, there's various ways to non-dimensionalize, and some are easier to analyze than others. So, for instance, we have a population here, N, which has units of budworms. We also have 2 characteristic populations in the problem. There's K, the number of budworms that the forest can support on its own, and A, the number of budworms at which the predation starts to turn on sort of sharply. So should we scale out N, should we divide N by A or by K? I mean, both are reasonable things to do. So 2 characteristic population sizes, both A and K. We're going to choose the scale of N. by the way, this doesn't affect whether you get the right answer or not. I mean, you can still get the right answer doing it the other way than what we choose. It'll just be easier if you do it the way I'm going to suggest, and I'll show what makes it easier in a minute. So we're going to choose the scale of n by this little heuristic argument. If I look at this dynamical system here with that p of n being this thing, this is kind of the nastiest term. It's the most nonlinear looking. And I want to choose the scale so that this term will have no parameters in it. That's going to be the strategy. Choose the scale of n to make the nonlinear p of n term have no parameters. So, all right, here's how it will work. That is, let's define a dimensionless population, x, to be, n over a. And then we have to convert everything into x terms. That is, n will be a times x, n dot would be a x dot. And so we have a dx dt. That's the first term is r. N is ax. 1 minus ax over k. Minus the p of n becomes b a squared x squared over a squared 1 plus x squared. Now we said that we want this nonlinear predation term, this one, to have no parameters in it for reasons that will become clear in a minute. So at the moment, well, for one thing, you can see that the a squareds cancel. That's good. There is still this b term. So to clean this up a little further and to make this have no parameters, let's divide the whole equation by b. So then this would become a over b dx dt is r a over b 1 minus a over k times x minus x squared over 1 plus x squared. So this is now a dimensionless equation, right? It has no units of any, well, or does it? Actually, the x is dimensionless, but time still has units, right, of days or weeks or whatever. So we would like to introduce a dimensionless time, and you can see how to do it by looking at this. That is, we introduce a dimensionless time. Let's let tau equal, it should be b times t over a. Did I make a mistake?
Yeah, you missed an x next to the RA over b.
What's that? I missed the x?
Yes.
Yes, I did. Thank you. Good. Let's put it here. Well, all right. It'll fit there. Yes, good catch. Thank you. Anything else there? Okay. Yeah, good. Thanks. So anyway, I was going to say, let's let time be defined, a dimensionless time, be b times t over a. Is that right? Yeah. So this is dimensionless time. And with all those choices, let's see what our system becomes. All right, so let's use prime instead of dot to mean time derivative with respect to dimensionless time. Then we have x prime is, so as I say, prime is dd tau. So x prime is, actually, you can sort of see now, maybe it's worth just circling some things. Let's go back here for a second. Notice all kinds of dimensionless groups. A over k has no units. That's a ratio of two characteristic populations. So let's call that 1 over k. But I'll use lowercase k to mean dimensionless object. It's a dimensionless version of the carrying capacity. Yes?
Why do you make it 1 over k?
Well, I could call it little a, but I wanted to keep looking like the logistic model. Because remember, what we're trying to do is we put all the parameters not here. We're going to shove them all into this term. And so I'm used to having k in a logistic model, so I'm calling it that. And then likewise, in my logistic model, I would normally have a growth rate r, which here you can see should be r a over b. And so those are now dimensionless growth rates and dimensionless carrying capacity. And then we get x prime is little r x, 1 minus little x over k is, no, sorry, then minus x squared over 1 plus x squared. That's my dynamical system. And notice, as advertised, it has 2 parameters instead of 4. We have somehow lumped the 4 into what are really essential. That is, as we change parameters, we can change the time scale, but that doesn't change the dynamics. And we can also change population levels, but again, that doesn't. Those are just scalings. The really essential parameters are these r and k. They affect what the system can do in the long run. You want to ask anything at this point, or you're still with me? Yes?
Would you lose some modes of taking parameters by putting them all to couple them together? So that way you can't have a full range of varying and see what happens.
Well, we haven't done anything. We've just, so the question was, by lumping parameters together, aren't we somehow losing something in the dynamics? And no, we're not in this case. That is, all that we're doing is changing a time scale or a population scale, but we are not changing the essence of what the system can do. And so this is a really deep principle that, I mean, you've seen this kind of thing. Like when you watch a Hollywood movie and you see the boat being tossed on the waves and it looks realistic. Well, but except it's not a boat. It's a little toy boat in a bathtub in some studio in Hollywood. And they've made it so that it's a properly scaled model so that the motion of the boat, even though it's many-fold smaller than the real boat, is accurate. If everything is scaled correctly, it will look right. So what we're doing here is kind of scaling to get to the, I mean, obviously if it looked wrong, that wouldn't be good Hollywood, good movie. But so scale models, are supposed to preserve the essential dynamics, but be at a different time or space scale. And that's what we're doing here. Plus, you could see at the level of algebra, we haven't done anything. We're just introducing definitions. Yes?
So is it true that the non-dimensionalization reduces your parameter space from, so you have like m different units to begin with, so you end up with m parameters in non-dimensionalization?
Okay, so the question was how many, maybe the question is, if I could rephrase it, something like, we started with 4 parameters. We ended up with 2 dimensionless groups of parameters. Is there some principle that tells us how many dimensionless groups we should expect? And probably you know the answer to this, I'm guessing. So there is a principle, right? I mean, engineers teach this, called, fancy thing, the Buckingham pi theorem. But the common sense thing is that I had 2 objects to play with, x and I had the population and the time. So I could play by rescaling population and time. You can see I did it explicitly. Here's time, population at the top, n over a. So by adjusting the population and the time, 2 things, I can subtract those 2 from the 4 I started with, leaving me with 2. So if you can non-dimensionalize, I mean, anyway, I haven't stated what the precise theorem is, but maybe you get the idea. As many things as you can non-dimensionalize that are like time or space or population, that's how many things how many parameters you can reduce out of the parameter space. Yes?
So it seems like originally you had all these parameters that could sort of describe both the dynamics of the worm as well as the bird. But now that it's non-dimensionalized, it feels as though, even though you had all these parameters to describe everything, like when appropriately scaled, it feels like it has to do so much to it.
Okay, so the comment is, although originally it looked like there was bird behavior somehow built into the model, or bird properties and budworm properties and forest properties, now it's all kind of lumped together in a way that it looks like the birds are gone.
But it's not that the birds are gone, but
They're implicit, right?
it's dependent on the logistic growth.
Well, they're built into the R and the K now in some way that, you're right. So the interpretation of this requires some care, because this is not just, everything is lumped in. These dimensionless groups involve several things. But if we think about it correctly, I'll try to give you some reasoning like that later. You'll see that we can account for the birds and the forest too.
It feels like the worms are kind of saying it's not about you, it's about me.
But the worms, of course, the worms are saying that. Yes, they are. The worms are saying it's about me, not you. But no, but the worms,
But I guess if we non-dimensionalize it another way, you could have
you can make it so the worms don't count. Right. I mean, we could have put all the parameters in here and then it'd be only about the birds. Yeah, but that's an illusion. It's about the whole ecosystem, and that's incorporated in the R and the K. Yeah. Okay, so now, here's this system. Can we analyze it? It's just a one-dimensional flow on a line. And so what can we see? One thing you can notice is that, x equals 0 is one equilibrium solution, right? If I put in, let's look at the fixed points first. I mean, we know that fixed points dominate the dynamics of these one-dimensional systems, and they really can't do anything but approach fixed points in the long run or go out to infinity. So fixed points where x prime is 0, that occurs when, for one thing, either x star is 0, excuse me, which of course means if there are no budworms, then there never will be any budworms. So that would be an equilibrium state. And so I notice we're neglecting migration, right? I mean, we don't have a budworm problem here in Ithaca, but if the budworms migrated over here, then conceivably we would. But anyway, that's been ignored. We're not thinking about that. And then there's a bunch of other fixed points. So let's try to understand what they would satisfy. So the other x star satisfy this equation. Dividing through by x, you have r times 1 minus x over k equals x over 1 plus x squared. And this is the equation I want to focus on now for a little while, because for one thing, it's what justifies or at least motivates why did we do the scaling that we did. I said I wanted to lump the parameters into the logistic term and take them out of the predation term. Why did I do that? Because now this is an easy term to interpret graphically. This is an equation of a straight line. Whereas this is some not so terribly familiar nonlinear function. And I think it's much easier to understand as I change r and k what the effect is. I'm just moving the intercept or the slope of the line. Whereas if I had the parameters here, it would be a little harder to see what they were doing. That's all. So let's analyze this. Now, you might say, why bother? Why don't I just solve it? This I could multiply across by the denominator, and then I would have a cubic equation in x. That's true. And so if you are still thinking the algebraic way that you're probably used to, you would just put this in Maple and solve for the 3 roots and get yourself totally confused. Because, as you know, the cubic formula is a big monster, and it's hard to interpret what it's saying. So that is not the right way to think. I mean, I don't find it a transparent way to think anyway. So we were going to do it graphically, as we do throughout the course. And so graphically, you would draw this picture to look for intersections of, well, first, this right-hand side, x over 1 plus x squared, let's think about that. For small x, it behaves like x. So it grows sort of like that. But then at large x, it will behave like 1 over x. Right? When x is large, this becomes approximately 1 over x. So it's going to look sort of like that. And so the curve sketch for the right-hand side is something that looks sort of like so. I've exaggerated it a little bit, but that's the idea. It's sort of like that. And the left-hand side, well, that has an intercept. When x equals 0, its intercept is r. And when x equals k, it goes through the x-axis. And so this just, of course, is a straight line. And then for the picture I've drawn, there's one intersection, which would mean one fixed point, in addition to the one we already calculated at x equals 0. So this is the, as I said, the graph of this is a line. Which is why we scaled the equation as we did. But the real payoff for doing things this way is what happens as we start changing r and k. That is, we want to see, I mean, you know, a cubic equation in principle could have 3 zeros. Whereas at the moment, we only have one real zero. We're not interested in any complex or imaginary zeros. Those aren't biologically meaningful. So we have at the moment 1, but you can see by changing the picture, you could have 3. Well, right, I mean, like it's conceivable that the picture could look like this. Where you'd then have 3. That is, there's one here. And I'll call this kind of root A when I have 3 of them. And then here's B. And then this one occurring way out here, we'll call C. So that sort of picture occurs when the line is very shallow. You can see that when the line is very steep, we're just going to have 1. Right? I mean, these are all sort of A-type roots. Low levels of budworms in biological terms. Whereas, again, if we're thinking biologically, then this is like a small level of budworms. This is some medium, intermediate level. And then this would be the outbreak. Right? This is a big whopping level that is undesirable, obviously, from the point of view of the forest, but very desirable from the point of view of the budworms. I guess. No, they don't care. They just care about themselves. But still, you can see from the picture that we get one intersection if k is small. And that's true for any r. Right? I mean, like, think about it. Suppose the k is a really small number, like, well, actually, the k I've drawn here appears to be small enough. For any r, that is, as this point moves up or down on this axis, you can see that the line is always going to intersect this curve in just one point. I mean, even when it's very large, it's still just hitting in the one point. What we're trying to understand now is how many roots do we get that is how many fixed points, as a function of r and k jointly. And so I'm saying one easy observation is that when k is small, for any r, we're just going to have one intersection. However, in a picture like this, remember k would correspond to this point. When k is big, then we can conceivably have 3 roots. And so we want to try to understand these transitions. How do we go from 1 to 3? Is there a question? Yes? Yes, that's not completely clear yet, but yes. I mean, I haven't really made the case that C is the outbreak, but we'll, yeah, I'm sort of getting ahead of myself there. But it will turn out that C is an outbreak. But I agree, that's not completely obvious yet, what the meaning is. Yeah, let me look at what happens actually for large values of k. So let's draw this picture again. So let me suppose the k is way the heck out here. I'm not really sure how to draw my curve to make this clear. Now, there's an issue of everything fitting on the blackboard. Let me try that again. Okay, so this is the x over 1 plus x squared curve. And then, all right, let's put a k here. So we know that if the line is very, very shallow like this, then we're just getting one intersection of this A type. Now let's imagine that we start increasing r. Think of having a knob and you're turning the knob and r is going up a little bit. Can you see something interesting that can happen? Like suppose the picture goes like that. Right, the first interesting thing is when that line becomes tangent to the curve. Otherwise, we're just moving this point up and we're you know, A is just moving around a little, so there's a quantitative change, but nothing qualitatively interesting is happening. The first interesting qualitative thing is when this dashed line becomes tangent. So let me see, is that about what I've drawn there? Yeah, maybe. Okay, so let's pretend that the dashed line is the one where it's first tangent at some place like that. Now, we know from earlier discussions that when we have a tangent intersection of two curves like that, that's a signal that a bifurcation is about to take place. It's actually happening at that moment because we've just created a new intersection, a tangent intersection. And if we're just a little bit higher than that, so let's say like this, then we now have three intersections. That is, in addition to a point that looks like an A, there's a point that looks like a B and a point that looks like a C. And so at the tangent intersection, we only had 2 points. It's as if the B and the C were together. And then as we lift up, B and C come apart. So what is that? When I created B out of nothing and then suddenly, actually I created B and C together and then they move apart. That's a saddle node bifurcation, right? So we have a saddle node bifurcation at the moment of tangency. And then watch what happens as we go still higher. Can you see the next interesting thing that will happen? It's right here. When we have a tangent intersection here between A and B, That's another saddle node bifurcation. And then finally, when we're at a very high value of R, then we only have C. So the point is that for large K, we can have 1, 2, or 3 intersections. And if we track what happens as R increases, we've gone from having 1 we went from 1, which was sort of this A type, then to having 2, which was A and a kind of BC merged together as a single object. Then we went to 3, which was an A, a B, and a C. Then we went back to 2 at this tangency here when A and B have merged into a single object. And then finally back to 1, which was just a C. So let me go back to the thinking about the diagram of a population flowing on the x-axis, because I think that will be clearer. Maybe before I do that, though, I should say that, from this picture, we saw that B is playing this crucial role. It's the thing that's colliding. It's either colliding with C over here or with A over there. So B can collide with A or C in saddle node bifurcations. Whoops, I went a little too far there. And that was occurring at critical values of R that depended on the initial K, not initial, but the value of K that we chose. So it's a sort of complicated picture bifurcation-wise, but one way you could summarize it is by asking in the RK plane. So now I'm in the parameter plane of R and K. Where do I have 1 root? Where do I have 3? Where do I have 2? This is a little bit of a more involved calculation than I want to show today, but you can look in the book if you want to see how to do it. The point is, if we just focus on where these bifurcations occur, they occur at certain RK pairs. Right, like here where I fixed this value of K, I had bifurcations when R was at this level, I have one tangency, and when R was at that level, I have the other tangency. So at that value of K, say it was like this, I would have 2 values of R where saddle node bifurcations occur. And then if we imagine sweeping the K, then what happens, it ends up that it looks like this, approximately. There's a curve of saddle node bifurcations and another curve of saddle node bifurcations, and those 2 curves meet at a cusp that is a corner where the 2 curves are not only intersecting, but intersecting tangentially. And then inside of here, we have 3 fixed points where when I say that, what I mean is I'm ignoring there's always this trivial fixed point at x equals 0. I'm only talking now about the 3 that are non-trivial that we get from this construction. So 3 fixed points besides the x equals 0 one. And so that would correspond like to one of these lines. You know, this one that has the 3 fixed points, A, B, C. It's got an intermediate value of R. Intermediate value of R, but a large K. And then we already saw that at small k, we only have 1 fixed point. That was this kind of picture up here. Small k, only 1 fixed point for each R. Right, that's over here. And then all around here, we also just have 1 fixed point. And when we cross through either of these lines, right on the line, we have 2 fixed points, one of which is a tangential, you know, a sort of this merged fixed point of the type I was calling either an AB or a BC. Okay, so if you want the details of this, like what these curves are in parametric form, check section 3.7 where it's worked out. But instead, I want to just focus on a qualitative remark, which is let's talk about the stability of these various points. And this gets back to the earlier question of how do we know that C really means an outbreak? Okay, so let's suppose we're in a regime where we have the 3 fixed points besides x equals 0. So then, now going to our picture where we look at, say, x prime, so the rate of dimensionless budworm increase versus x, that is drawing our usual kind of picture. I want to analyze our dynamical system up here, this one. X prime is Rx. 1 minus x over k minus x squared over 1 plus x squared. Look at this for, if x is close to 0, you can just see in your head what's happening. If x is close to 0, the parentheses is close to 1. This is basically Rx. This term is negligible because it's quadratic in x for small x. It behaves like x squared. So the linearization of this about x equals 0 is just Rx. And Rx means that we're having exponential growth for small populations, which makes sense. When the budworms are at a low level, remember the birds don't really see them, and they'll just grow more or less exponentially. So the claim is that x equals 0 by linearization is an unstable fixed point. And that means that x prime is coming out of there with a slope r. What I'm trying to do is sketch the whole right-hand side of the x prime equation without doing any work. So it's got to start with a positive slope. And then I claim, although I'm not proving it, but I hope it's common sense, that the stability of the fixed points has to alternate. That is, this cubic, or not the cubic, but that nonlinear right-hand side of x prime has to do something where it goes kind of like that. That is, we're going to have these other 3 fixed points, but this one has to be stable because this one was unstable at the origin. So we're going to the right, we're going to bang into this, and then the middle one has to be unstable. I mean, they have to alternate stability. You can think about that for a minute. That's sort of topologically clear, I hope, that you can't have a situation where you have a stable fixed point and a stable fixed point on the line as neighbors, because the flow would be going towards this one that way and towards this one that way. And that's clearly going to cause a problem if there are no other fixed points in between. I mean, there has to be an unstable fixed point in between if the vector field is smooth. Otherwise, you know, right, you can see this thing is pulling itself apart. Or another way to say it is that x dot is negative here and positive here. So it has to be 0 somewhere in between by continuity. So anyway, you can't have the fixed points with a stable next to a stable. for the types of vector fields we're considering. So we have to, without doing any work, we know that the stability is unstable, stable. A is stable when it exists. B is unstable when it exists. And C is stable. And so these are the ones I was referring to as C is the outbreak level. A is what the biologists would call the refuge level. That's like the budworms are sort of hiding or not really noticed. And B is a threshold in the sense that if you're above the level B, if there's more budworms than B, then they will continue to grow until they reach C. Whereas if you're below B, they will go down back to the refuge level. Is there any question? Yes?
If you're injecting something like that with only 2 fixed points, how do you know one of them is not a bifurcation?
Well, I was assuming, I mean, if I had only two rather than 3, if I had 2, then one of them would be at a bifurcation, and I would have to think harder. Yeah. You know, I don't want to, yeah. We're sort of just trying to do the simple case of 3. But actually, let's talk about 2, because we should try to understand a little bit what happens as we change parameters. Incidentally, I mean, maybe I've made it sound more complicated than it is. If you just want, you could always graph the right-hand side by just being either plugging it into a graphing calculator or just thinking about it and doing curve sketching. I mean, this shape is not that hard to calculate by just thinking about it. And then once you have that, then you know where the slope is negative. That's giving you a stable fixed point. OK, but anyway, so the interesting thing is I mentioned that this problem can illustrate jump phenomena. And let's see how that works. Let's think about what happens as we're in this regime where we have 3 fixed points. But now let's change the parameters and start approaching one of those saddle node bifurcations. So you can get the jump phenomenon after a saddle node. So suppose that X is at A, that is, the population is at this low level, and the parameters start to drift for some reason. Ludwig and company in their paper give an argument about why you would expect the parameters to drift on a longer time scale. So let me first draw the picture. Here's X prime. We started with this kind of situation with our 3 fixed points. And suppose that as we change, well, like for one thing, as the forest gets older and the trees continue to grow, they're going to have more foliage, more leaves. And so Ludwig and company argue that as you have more leaves, in fact, the parameter that we called big A will grow. Maybe I should try to flesh this out a little bit. This is kind of an aside, but I think it's interesting. So as the forest ages, R increases slowly. And why do we say that? Well, Remember what little r was. I mean, this gets back to the question of whether we've lumped everything into these dimensionless groups. So if you remember, the definition of little r was big R times A over B. And think about this parameter big A in particular. So big A, which meant that was the level, the total population of budworms at which the birds would start to notice them and start gobbling them. And so the biologists say that the big A, which is sort of, it should be proportional to the surface area of the foliage. That is roughly like just how many leaves there are and how much surface area there is. And it's argued to be that you can think of that as, well, or Ludwig writes it as some other quantity, A prime. It doesn't mean derivative, it just means, he refers to this as the critical density per leaf, meaning critical density of budworms per leaf. So what am I saying here? That it's A prime times the surface area, or think of S as the number of leaves. Remember earlier I said that the birds are attuned to do density. How many budworms per leaf? Once that exceeds a critical number for them, they get interested and start eating. And so if you think of this A prime as whatever it takes to get the budworms interested, but then S is slowly growing as the forest ages, right? Number of leaves is growing. The forest is getting older and bigger. So this is growing slowly. That means that A will grow slowly, which means that in here, assuming R and B don't change, that little r will change on the time scale of the forest. So that's the argument. Well, I don't know if I said it very well, but so this is supposed to motivate looking at these curves, imagining that little r is slowly drifting. And so if you do that, then back in this picture up here, think of what happens as little r goes up slowly. What it says is that these lines are starting to pivot around this point K going up. And so B and C will be approaching each other. Is that right? Did I do that right? No. I want to think about being in the regime where there's 3 fixed points. As R goes up, A and B will approach each other. Right? I go from a picture like this. I'm rotating this line up to more like that. So if you think of this as A and this as B, they've now gotten closer together. Yes? K? Whoa, that's interesting. So you're saying K will also be moving? But K was, what was K? Little k was big K over big A. So you're saying as big A increases, then little k will decrease. So in fact, what's happening is that the line is moving. This is going up, but this point is also moving that way. I don't think it will change anything. We're still going to get these 2 points moving closer together. But that's an interesting point. It would do that. So what it will mean in this picture, though, is that the A and the B are coming closer together. And so you're going to get something qualitatively like this. Well, I mean, at the tangency, this will just be tangent here. Say, something like that. Like, just imagine sort of lifting this up. And then just past the tangency, this will now no longer touch the axis, whereas this will still touch over here at C. So what does this mean? That the system which was sitting here at A, like I said, suppose X is at A, you know, everybody's happy with the forest. There hasn't been an outbreak in a long time. And then as we lift this up, once we go past the tangency, you see this point doesn't exist anymore. There's no intersection. And the system has no choice but to jump discontinuously over to here or somewhere over there. That's what I mean by the jump. That you've changed R continuously, yet you had to jump because A has disappeared all the way to C. Yes?
Isn't that heavily dependent, though, on the relative size of K and R over V? If the little k moves to the left more quickly than the R increases, then you get the saddle more by the other.
Yes, so the question was, isn't it dependent on the details of the R and what the A and the B and their relation? Oh boy, lots of hands are going up. That as you change the which one? The big A, then it seems like both R and K are changing, so it's confusing about what's going to happen. I mean, it's true. I hadn't really thought about that, and the analysis is usually just phrased in terms of imagine little r drifting while holding little k fixed. Though if this is the reason for little r drifting, then I think I do have a bit of a problem. So there's a bunch of hands. I hope you're rescuing me and not making more trouble. Okay, go ahead.
You could imagine that big K and big A will track, though,
Big K and big A might track each other.
where big K is like the carrier capacity, which
Oh, that's a good argument. Thank you. The argument is, you might expect, if the argument is that big A is proportional to the number of leaves, so would big K also be proportional to the number of leaves. So in fact, this effect might leave little k more or less constant, whereas R would be changing. I like it. I like it. Thank you. Good save. And I think actually Ludwig and company might have said that in their paper, and I might have just forgotten it. So yeah, that's good. Okay, so thank you for the save. And anyway, but did you get the main point? That we were at A, and then we jumped. Now, there's one other important qualitative point here, which people who aren't used to nonlinear thinking would find this kind of surprising. But hopefully you will not be too shocked to hear it. That let's suppose, I mean, just to make it dramatic and inject a little politics here. Like, let's suppose that there's some government policy which has the effect of changing the R. Like maybe we decide to start using some pesticide, or we've deregulated some industry, or we've done something. Okay, so everything was good in the forest. Then the new policy comes into effect, and suddenly, whammo, there's an outbreak, and it's terrible. And then the environmentalists or the timber people who are all upset say, it's no good. Whatever policy changes you made were terrible. We need to go back to this curve, the way things were in the good old days. Do you see what's interesting? That you go back to the old ways as far as the curve is concerned, but the system does not go back to A. You were at A, you put in the new policy, you jump over to here, you say, oh my God, that's terrible. Let's go back to the old ways. You go back to this curve, well, that only brings you to here. Right? Because that's the locally stable point. You can't get all the way back to A. The system is not reversible under this policy reversal. In fact, if you want to go all the way back to A, you would have to do something much more radical. You'd have to bring this curve, to a place where this bump is now below the axis, right? You'd have to go to something that looks like that. So this is a kind of non-reversibility with respect to changing parameters that people call hysteresis. And it's a big deal in nonlinear systems. So you get the hysteresis effect if the parameters, as I say, so if you change the parameter R and cause a jump from A to C, then reversing the parameter does not, at least for the case we're discussing here, does not bring you back to A. So there's this lack of reversibility is a common thing in nonlinear systems. And I want to try to illustrate it, although this is a difficult picture to draw. And I've drawn it in section 3.7, so you can look there. But let me just try, and you can try, because it's an important picture. That is, you can visualize this lack of reversibility as what people call a Cusp catastrophe. That is, there's a certain surface on which this will all be hopefully kind of clear. Now, what I'm going to try to draw is a three-dimensional picture where x star will be vertical, r would be horizontal here in the board, and k is coming out of the board. Okay, so I can't draw that, but that's what that's supposed to mean, that k is the third dimension coming at you. And so now here's my attempt to draw this surface. So this is supposed to look like a pedestal where I'm going to erect the surface. Okay, here's the attempt at the surface. The first thing to draw is the beginning part, which goes up and around and like that. Then going back, it comes back like this, and then here it sort of just kind of goes up more or less like that. So what you're supposed to picture here is something that kind of looks like a carpet with a fold in it, except the nature of the fold is that here's a piece of it, and then there's another piece tucked under here that's visible to your eye, and then you know, I can't really show it, but there's still kind of a fold under there. Now, what am I trying to show? Actually, let me finish. The rest of the pedestal has this base that goes back like that. And does that look like anything? Sort of see what's going on? So what am I saying? Here's the picture, you know, happening on the surface. I said, here we are. This is kind of A down here. We're happy. Everything is good. Notice the picture. This is K. We're at a high level of K out towards us this way. K coming out this way. So we're blithely moving along in R, going this way. Everything's fine. We're moving along the surface until we come to this place, and then, whoa, we jump up to this upper sheet, causing us to be up here. This is where the C's live, and we're moving this way now. And then people say, oh no, that's terrible, let's go back. So you go back, and now you're moving this way, except what I was claiming is that the place where you were caused to jump up, you're not going to jump down. You're still on the top surface. And you won't jump down until you get all the way back to here, and now you can finally jump down. And so that's a hysteresis loop, which we can visualize as happening down here. So, I mean, if I take this whole surface and project it down, then what you would see, remember I drew this picture up here? This is supposed to be the projection of this surface down onto the bottom RK plane. That is, there would be something that looks kind of like this. This is where it really is hard to think about. There's this, and then this going back, and then it's kind of underneath. No, it doesn't look nice the way I drew it. But back here where these two folds are joining, that's the cusp. And so this motion has been happening down here in the parameter plane. We went that way, and then we went back. But really, the response is happening up here on this folded surface, so that we've jumped up and then gone. Do you see what? I don't know. I hope that worked for you. If not, consult the picture in the book. But I was trying to make the point that this hysteresis loop is this picture going up and around and then back. And it's a fundamental thing that can happen. You can see even in this simple nonlinear system, and it certainly happens in the real world. All right, so let's stop there. Now, I wanted to hand back your homework. I don't have a good system for this, so just come up here and go at it.